Hello. In this video, we are going to kick off our series on classical mechanics, where we will be dealing with the Lagrangian and Hamiltonian dynamics, and then also further into the case being we have already discussed about the two bodies central force problems, the variational principles, and so on. But before that, we would like to provide an introduction to what exactly are these things, the new terms that we will be coming across right after the junior level physics. Now, the mechanics as we know it involves physical objects in rest or motion, and they are at rest or motion, and they are under the influence of the external and internal interactions that are taking place. Now, the mechanics that is based on Newton's laws of motion, and alternatively it has been developed by Lagrange, Hamiltonian, and others, is what we call as classical mechanics. Now, the mechanics dealing with Newton's laws and their consequences are known as Newtonian or vectorial mechanics. The reason being vectorial mechanics because the quantities that are involved in this scheme of things are the vector quantities, namely force, acceleration, momentum, etc. But alternatively, and a much superior scheme in classical mechanics was then developed by D'Alembert, Lagrange, and Hamilton, and many more, and that constitutes what we term as the analytical mechanics, where the quantities that are used are the much simpler scalar quantities, like the case being energy, and the dynamical relations that are provided in that are obtained by the systematic process of differentiation, which makes it much more approachable. Now, the advantage of the analytical mechanics is that it can be generalized to quantum mechanics, where the Newton's laws they give up in the quantum level. Remember, in the quantum level, the things get shrinked. I mean, we are dealing with classical mechanics, of course. The classical mechanics will but provide, the analytical approach will but provide a scheme that will be applicable in the quantum mechanics, the classical mechanics being dealing with magnified macroscopic objects, while the quantum mechanics dealing with miniature small scale micro objects. But still, the scheme is provided by the analytical approach that we will be discussing in our approach to the mechanics, to the classical mechanics. Now, in 1905, when Einstein gave the experimental facts related to the constancy of the speed of light in vacuum, he proposed the special theory of relativity, as popularly known as the STR, special theory of relativity, which modifies the classical ideas of space and time and deals with all particle speeds. Now, the relativistic mechanics of Einstein yields the result of Newtonian mechanics at relatively low speeds. So, this special theory eventually at lower speeds, or at very low speeds, that changes to the case of Newtonian mechanics. And, uh, and however, the relativistic theory of Einstein, it does not modify the classical ideas regarding the basic nature of matter and radiation, and hence it is often studied in classical mechanics. So the STR that we are speaking of, that will be covered in our classical mechanics portion as well. Now, classical mechanics is often found to be inadequate to describe the behavior of particles of microscopic size, such as electrons that are present in atoms and nuclear particles, etc. For the description of small scale phenomena in the atomic and nuclear physics, we have the quantum mechanics, which has been formulated when applied to large bodies, gives the results obtained in classical mechanics. So there is a link between the classical and the quantum, that when the rules of quantum mechanics are applied to the macroscopic objects instead of the microscopic, obviously the rules are made for the microscopic objects, but when they are applied to the macroscopic objects, they yield the result that have been obtained in classical mechanics. So in all, we see that classical mechanics does provide us with a lot of things, a lot of information in depth. And before really moving over to the core of classical mechanics, we would like to discuss some introductory ideas related to classical mechanics, which we might be aware of from our previous lower levels of the studies that we have made so far in higher secondary or junior levels. We'll be just going through them, summarizing them in small bits. Then we'll be moving over to the important topic in the upcoming videos as well. Now, firstly, in the case of introductory ideas, it is expected that we know a bit about space and also we know a bit about time. It's assumed that the space and time are continuous, and that the motion of a particle in space is described by knowing the position at different instants of time. And also the case that there are universal standards of length and time, that the units of measurement of length and time are usually considered in meters and in seconds. Now, if a physical phenomenon that occurs in space, that is, it has a position which is at a known point and the time of occurrence is known, then the point taken together with the position and the time, we call it an event. And if there are two observers who have synchronized their clocks, will always agree about the time of an event, and that the geometry of space is Euclidean, and that there is no limit in principle to the accuracy with which we can measure the position and the momentum. That's for the macroscopic objects, obviously. Then next we consider the cases of the homogeneity of space and time. Now, homogeneous means it does not really change, it's evenly distributed throughout. So that is the case with space. And what does the homogeneity of space lead to? Well, the homogeneity of space always results in the conservation laws related to the conservation of the linear momentum and the angular momentum, while the homogeneity in time means there is no variation of that quantity with, or the variation of that quantity with respect to time, then that deals with the conservation of the favorite term called energy. That energy remains constant throughout the time. So that's what we deal with in the case of homogeneity of space and time. Now, to give you a picture of how exactly are we dealing with the different parts of the mechanics, we can provide you with a simple diagram which tells us that if we divide this into the parts that we have discussed, that is, we divide this in with speed and this axis with the size, then for speeds we'll be taking two segments: the speeds which are below 3 times of 10 to the power 8 meters per second, that is the speed of light, of course, and the speed greater than 3 times of 10 to the power 8 meters per second. Then again, for the sizes, we consider two basic cases, that is one with size greater than 10 raised to the power minus 9 meters and less, that is in the angstrom scale, that is 10 raised to the power minus 9. Actually, angstrom is 10 raised to the power minus 10, so that is obviously smaller than 10 raised to the power minus 9. So, and as an example, I can set here the angstrom scale, and these are the scales which are above. And here obviously we are dealing with the non-relativistic on the left hand side and the relativistic cases on the right hand side. As far as the case of non-relativistic as well as the macroscopic objects are concerned, what we will be studying is all of that will be covered in classical mechanics. And as far as the case of higher speeds are concerned, that is that is the relativistic cases, that is speed greater than 10 raised to 3 times of 10 raised to power 8, or even comparable to that, that is in relativistic. Well, obviously there is a nothing greater than the speed of light, so we'll probably provide you uh, this greater than sign. Well, we'll exclude that for now. We will take a nearly equivalent sign for that. So this is in relativistic mechanics. And then for quantum mechanics, we have the cases that will be the first cases that we deal in quantum mechanics are the non-relativistic cases, but for microscopic objects, again going to the level of angstrom or even lesser, that is the Fermi scale, in case of the electrons within the atom. And then we have the case of the quantum field theory, which again deals with the higher energy and the higher cases of velocity comparable to that of the speed of light, but also dealing with the microscopic, or so as to say the nanoscale. So that's it, our discussion about the introductory ideas in this video. We'll be continuing with the introductory ideas in the next video as well, with a few cases, few numerical cases, problems that were dealt with, basically the single particle system and the multi-particle or the many particle systems. Now, one thing you should know is that the Newtonian mechanics that helps in dealing with forces between the two objects, but when it comes to three objects or more, the Newtonian mechanics gets complicated, and we'll see about the complications that arise and how later on with the analytical mechanics involved, how do we get rid of those complications. We'll be dealing with that, but that is to come in the upcoming videos, so stay tuned for that. Till next time, thank you for watching.